Hi, in this video I would like to share some information regarding hardness. Hardness per se is very much difficult to define. In mineralogical terms, hardness is defined as the ability of a material to resist scratching. In metallurgical terms and in other disciplines, hardness is defined as the ability of a material to resist indentation. So this resistance to indentation concept forms the basis on which various modern hardness tests are being designed. Hardness provides valuable information to the dentist, and hardness tests are included in various ADA specifications for dental materials also. We have various hardness tests like Brinell Hardness, Rockwell Hardness, Shore, Barcol, Knoop and Vickers, etc. So all these hardness tests can be broadly classified as either macro hardness or micro hardness tests. Now let's briefly look into the differences between these two, that is macro as well as micro. So in macro hardness, first let's see the examples of this macro hardness as well as micro hardness tests. In macro hardness tests we have Brinell Hardness, which is represented as BHN, Brinell Hardness number, and Rockwell Hardness number. So both Brinell and Rockwell come under macro hardness, whereas Vickers Hardness, which is represented as HV, and Knoop Hardness, which is represented as KHN. So both Vickers and Knoop come under micro hardness. Basically all these hardness tests employ a common principle. For example, if we want to test the hardness of this particular material, we need to have a specific shape indenter and a load is applied on the indenter. For suppose this is the indenter and I'm trying to apply some amount of load. So at the moment I apply some amount of load here, we can see some kind of indentation in the material which we are testing. So the amount of load applied, if this load is less than if this load is less than 9.8 Newton, and once the indentation is formed on this material, if the depth of this indentation is less than 19 microns, then those tests which are employing this come under micro hardness. So micro hardness, as it includes Vickers and Knoop, do employ a load of less than 9.8 newtons and the depth of indentation is less than 19 microns. So this is the major difference between macro hardness and micro hardness test. Now let's go into the details of each hardness test. So first we'll deal with Brinell Hardness test. So for sake of convenience, let's divide each hardness into certain subheadings. First one is abbreviation, and second one is shape of indenter, and third one is formula, like how we calculate the hardness, and last but not the least, examples like what materials are being used in order to evaluate the specific hardness. So coming to the abbreviation of Brinell Hardness number, it is abbreviated as BHN. And the shape of indenter which is employed in order to evaluate a given specimen is hardened steel ball. So a steel ball is used as an indenter in case of Brinell hardness. So the formula which is employed in order to calculate Brinell hardness number is load divided by area or diameter of indentation. I'll explain you this in detail now. So in Brinell hardness, what happens is, for example, we are given a material X. So we need to evaluate the hardness of this material. So what we try to do is, employing the Brinell hardness, we take a stainless steel ball which is attached to a specified load, which is denoted as N. The load is denoted as N, and this steel ball is made to press against the surface of the material which we are going to test. In this case, it's X. The moment we press this ball against this material, we can expect a round indentation area on this material. Since the shape of the ball is round, the indentation area which is found on this material will also be round. So in order to calculate the Brinell hardness number, we use the following formula: load which we are placing divided by the diameter of this indented area. So we'll calculate the diameter and we'll enter it here. So through this process we obtain Brinell hardness number. So the smaller the area of indentation, the greater the Brinell hardness number, the more hard the material is. So if the Brinell hardness number is more, it indicates that a material is very much hard. So which is evident from this formula. And what all materials can be used to evaluate their hardness using Brinell hardness number? So Brinell hardness number evaluates the hardness of metals or various metallic materials which are being used in dentistry. So this is in brief regarding Brinell hardness number. So while discussing other hardness tests, let's discuss them in the same format. So Brinell hardness number, to summarize, is represented as BHN. The shape of the indenter which is being used here is steel ball, and the formula which we use in order to calculate the Brinell hardness number is the amount of load applied divided by the area or the diameter of the indentation. And what are all the materials which we can use to evaluate the hardness of materials is metals. So examples include metals. So metals hardness can be evaluated using Brinell hardness number. So this is in brief regarding Brinell hardness number. Now moving on to the next hardness, that is Rockwell hardness. So in Rockwell hardness, the principle more or less remains the same. So now let's discuss Rockwell hardness under the same headings. So I'll just briefly write down as Rockwell. So this Rockwell hardness is abbreviated as RHN, and the shape of the indenter which is being used in Rockwell hardness is same as that of Brinell hardness, that is either a steel ball or conical diamond point. So the shape of the indenter can be either a steel ball or a conical diamond point. So the formula which we use here in order to calculate the Rockwell hardness is also the same. That is, Rockwell hardness number is given by the following formula: load divided by depth of penetration of indenter. So if you closely observe, this is varying. So in case of Brinell hardness, the area or diameter of indentation is being measured, but in case of Rockwell hardness, the load is being divided by the depth of penetration of the indenter. For suppose if you have a material X, if you assume that a conical diamond point indenter is being used, the moment when we are applying with specified load, that is N, so when we are applying or pressing this indenter onto the surface of X, what happens is there will be a dial gauge on this entire indenter. So this dial gauge directly measures the depth of penetration of this indenter into the material. So if we observe closely, the value which we obtain here is comparatively easy. That is, Rockwell hardness is easy to measure compared to Brinell hardness, because here the depth of penetration is being given by the device itself as it contains a dial gauge. So compared to Brinell hardness, it's more convenient. So in order to summarize Rockwell, it's abbreviated as RHN. It employs either a steel ball or a conical diamond point as an indenter. and it's given by the following formula, that is load divided by the depth of penetration of the indenter, which we have discussed here. So to discuss another point, both Brinell Hardness as well as Rockwell Hardness cannot be used to detect or to find out the hardness of brittle materials. This is very important. So brittle materials cannot be used to evaluate their hardness using these hardness tests. So that has to be kept in mind. Now moving on to the other hardness tests, that is Vickers Hardness and Knoop Hardness. In case of Vickers Hardness, both Vickers Hardness and Knoop Hardness come under Micro Hardness tests. As I discussed earlier, Vickers Hardness and Knoop employ a load of less than 9.8 Newton, and the depth of penetration of the indenter is less than 19 microns. So now coming to the third test, that is Vickers Hardness. So I'll write that as Vickers. So Vickers is abbreviated as HV. So this is slightly different, so we need to keep that in mind. So Vickers Hardness is represented as HV, and the shape of the indenter which we use in Vickers Hardness is square based pyramid. So I'll draw the diagram so that you will get that easily. And the shape of the indenter, as we have discussed, is square based pyramid, and the formula which we employ here is the same, that is Vickers Hardness is obtained by dividing load by the area of indentation. So Vickers Hardness is obtained by the following formula. And how do we exactly perform this procedure? Again, take a material X whose hardness has to be evaluated. As I said, the indenter shape is square based pyramid. So in two-dimensional view it will be more or less like this. So here a specified load is applied, and once this square based pyramid indenter is made to press on this material, we obtain indentation of following shape. So square shaped indentation is obtained on this material when this indenter is pressed. So the area of this indentation has to be calculated. So this is done by measuring and taking the average of these two diagonals. So we'll measure the length of these two diagonals, take their average, and note that here. As we know the load, we can obtain Vickers Hardness. So I hope you understood this. So Vickers Hardness is calculated using this procedure, and the materials which can be used to evaluate Vickers Hardness, examples of materials whose hardness can be evaluated using Vickers Hardness is dental casting gold, that is gold alloys, and also brittle materials such as tooth structure. So the hardness of tooth structure as well as gold alloys can be evaluated using Vickers Hardness. I hope it's clear. So to summarize it, Vickers Hardness, abbreviated as HV, uses a square based pyramid as an indenter, and it's calculated using the following formula: load divided by the area of indentation. The area here, or the shape of indentation, is square, and the area is calculated by measuring the diagonals of this square and then averaging them and then employing that value here. So that's how we obtain Vickers Hardness. And the examples of materials where we can evaluate Vickers Hardness is dental casting gold alloys and also brittle substances such as tooth structure. So this is in brief regarding Vickers Hardness. Now moving on to the next test, that is Knoop Hardness. So Knoop Hardness is also a micro hardness test. So Knoop Hardness 4, write that as Knoop. It's abbreviated as KHN, Knoop Hardness number, and the shape of the indenter which is used, they haven't really mentioned the shape in Phillips. They just mentioned like a diamond tip tool of specific dimensions is used in Knoop Hardness. Diamond tip So using this we evaluate the hardness. So using the same formula again, that is Knoop hardness number given by load by divided by area of indentation. So this is how we obtain a Knoop hardness number. So the examples of materials, where the materials whose hardness can be evaluated using Knoop hardness is enamel, or again the same as that of the previous one, that is Vickers hardness, where we can evaluate the hardness of brittle materials. So the hardness of tooth enamel can be compared to that of either gold, porcelain, resin and other materials. And most importantly, the load which we apply in Knoop hardness, for suppose as I mentioned earlier, a diamond tip tool of specific dimension will be applied on a material, that is X, using a specified load. So the load which we apply in Knoop hardness varies from 0.1 kg to 1 kg. So we can see a lot of variation in the load. So it implies that while employing Knoop hardness, any material which is either extremely hard or extremely soft can be used to evaluate their hardness using Knoop hardness number. So that's the main advantage of Knoop hardness number. And most importantly, Knoop hardness is independent of the ductility of the material which you are using. For example, this material has certain ductility. So the value of Knoop hardness is independent of the ductility of the material which we are using, which I'll explain now. So this is very important, because when we are using a diamond tip tool of specific dimension, we are taking a material X whose hardness has to be evaluated. So when this diamond tip tool with specified load is pressed onto this material, we obtain an indentation which is rhomboid in outline. Please note this point. So when we press this load onto this material, we obtain an indentation which is rhomboid. Let me draw this again. So rhomboid is something like this. So in rhomboid we have a minor axis and a major axis. So this is the shape of the indentation obtained when load is applied. So when I said that Knoop hardness value is independent of the ductility of the material, it can be explained in this process. So the moment we are applying load and we are removing the load, there will be elastic recovery within this material along the minor axis, and this long axis remains unchanged in a given material. And we are using this long axis, we are measuring the length of this long axis and employing it in the formula. As I said, Knoop hardness number is given by the formula load distributed by the area of the indentation, which is nothing but the length of longest diagonal which is present in the indentation. So this longest diagonal is measured and it is placed here, and that's how we obtain Knoop hardness number. So the moment we are removing this indentation, there will be elastic recovery within this material only along the minor axis. It's because stresses are being distributed in that fashion, and as a result of which the long axis of this indented area remains unchanged, as a result of which Knoop hardness number doesn't change. So this Knoop hardness number, again I would like to repeat, Knoop hardness number is independent of the ductility of the material which we are testing. So I've explained this, hope you understood, right? So this is in brief regarding various hardness tests, and apart from this we have other hardness tests such as Shore and Barkol. So apart from these regular hardness tests, we have other tests such as Shore and Barkol. Shore test is used to evaluate the hardness of elastomeric impressions, whereas Barkol is used to evaluate the hardness of resin composites. So both these tests also employ the same principle of working, that is a spring loaded indenter is used and it is applied or pressed onto the material which we are going to test, and the calculation part is also the same, that is the amount of load which you are applying is divided by the area of indentation. So this is in brief regarding various hardness tests. So to summarize, we have we need to understand that hardness is nothing but the ability of a material to resist indentation, and we have broadly divided hardness into macro hardness and micro hardness, and the criteria for differentiation is very important. That is the amount of load being used and the depth of indentation which is caused as a result of using these tests. And apart from that, today we have discussed various hardness tests, that is Brinell Hardness followed by Rockwell, and then we have discussed various micro hardness tests such as Vickers Hardness and Knoop Hardness tests. So this is in brief regarding various hardness tests. I know it's a bit difficult to understand this topic. The reason why I chose this topic in today's video is because while I used to prepare for my undergraduate exams or PG entrance, I never touched this topic, and fortunately or unfortunately I got several questions during my entrance examination. So understanding the concept is very important because we get to have many questions from this topic. So once you understand the concept, just leave it. You don't need to really remember all the stuff. Just try to understand the principle, the working principle behind this, and once you understand the concept, just revise it and then leave it. So before exam, if you just skim through the topic, you'll easily grasp because you have understood what the working principle behind this test is. So this is in brief regarding hardness test.